When working with switching converters, one of the key elements is the silicon. You'll find it in the switches as well as in the control circuit. As this is the main switching and control bit, it's an integral part of the noise generation mechanism. Hello and welcome back. So the first thing I want to look at today is the rectifying element, the diode, a component with an apparently simple function. Allow current to go one way, but not the other. Things aren't that simple though. Now, just as a side note, you do have synchronous converters where the diode was replaced by an extra transistor, so it may seem that the diode discussion does not apply to such a converter. However, in a real circuit, where the transistor switching is non-instantaneous and not perfectly predictable, a dead time is foreseen to prevent cross-conduction. At this very moment, the current through the converter does not suddenly stop, but rather it will be passing through the transistor's built-in diodes. In particular, for the synchronous buck converter, the current will be passing through the S2 diode. Now, when this is not acceptable, extra diodes are also added. So now, coming back to the diode, the fundamental property of interest is that it passes current one way, but not the other. And under static conditions, this is what mainly happens. Now, for today's noise discussion, there are two important unwanted properties that occur. First, the diode has some parallel capacitance, and this capacitance is reverse voltage dependent. This is the useful property of a varicap or varactor diode, but this is also an unwanted property in a rectifying diode. And the other important aspect to consider is the switching speed. So if we apply a voltage square wave, one that produces both a positive and a negative bias to a diode, we would expect that the diode conducts during one period and blocks during the other. However, the diode is not capable of instantaneously blocking a flow of charges. So for a short period of time, it will be conducting the wrong way. This can be quite problematic from an efficiency point of view, but it's also quite a noisy phenomenon since the pulse transitions occur quite fast. So, to highlight this behavior, first I created a set of boost converters where different diodes are used. The switch is always ideal, but for the diodes, I'm using multiple models, starting with an ideal one. So, let's just run this circuit and check the various behaviors that are appearing. First up, the ideal diode, which has no capacitance and no reverse recovery. If we look at the current through it, well, it's ideal. The diode is conducting one way, we have a positive current, but it's not conducting the other way. So, no real surprises here. Next up, if we look at a Schottky type of diode, which is considered to have negligible reverse recovery time, but it also has a non-negligible junction capacitance. For this particular model, a value of 90 picofarads is specified. When we look at the current through it, we start to see our reverse current in action. Right when the voltage changes polarity, there is a momentary reverse current, which in this case is about 240 milliamps. And the pulse itself is a few nanoseconds long. Now, if we look at another Schottky diode, this time one that has a larger capacitance, about 282 picofarads, and we check out the current again, things are getting a bit worse. So the reverse current becomes larger, but also the duration has been extended. Now, Schottky diodes are not the only type of diode that you'll find in use, so the next thing to consider is a fast recovery rectifier, which is a PN type of diode. And well, these are fast recovery, but the fast part is quite relative. With this particular model, we can see quite an increase in this current spike, as well as in the total duration. Now, if we zoom in for a moment, another thing that we'll notice is that the shape has also changed. So while the reverse current was happening because of the capacitance, we had a rather smooth increase and decrease of it. But when we have the reverse recovery of the diode, while we have a rather smooth increase, the decrease is far more abrupt. So even if the two waveforms would be of the same amplitude, the abrupt one would have a far larger noise spectrum, since it would extend to higher frequencies. Finally, we have the standard type of rectifier, and well, this is not fast at all. Both the current and the duration have increased quite a lot. So this is the type of diode that you shouldn't really be using in a switching converter. So finally, based on how fast the diode switches and how much junction capacitance there is, you will get a smaller or larger issue with your reverse current. Now, the effect of this reverse conduction is not just visible in the diode current, but also in the converter's voltage. So I took just a couple of the circuits from before and changed the output capacitor. So first off, if we just add in a bit of equivalent series resistance, and we check the operation of the circuit, the output voltage of the ideal diode converter is a trapezoid waveform. However, if we have the same circuit, but this time with a more realistic Schottky diode, other than the voltage variation, we are also seeing a sharp voltage spike appearing when the reverse current is occurring. Now, if we modify the circuit further, and also add in a bit of series inductance to our capacitor, and while we have a look again at the ideal diode condition, we are already seeing some oscillations. However, if we also check out the sharp spikes caused by the realistic diode, these oscillations will become far worse. So, just to highlight the effect of the diode switching speed, I have a small boost converter here, and for the diode, I used a socket just to be able to easily change it out. So normally you should not use sockets like this. But anyway, at the moment, I use the Schottky type of diode, the SR250, which is placed inside. Now, this particular diode does have a bit of a junction capacitance, but since it's a Schottky, it should not have any sort of reverse recovery time. Anyway, if we now turn on the converter, we can check the output side noise using the yellow channel of the oscilloscope, and we can see that a rather large oscillation is appearing. Now, we can confirm that this is occurring when the transistor is switching on, so when the diode should stop conducting, by also looking at the switching node. So, as expected, on the blue channel, we can see that the switching node has the high-to-low transition exactly when this spike is appearing. Now, other than this, we also have a clear oscillation on the turn-on side. So, because of the rather large capacitance of the diode, coupled with the various inductances in the circuit, we are getting quite a bit of ringing. However, if I now remove this diode and go for a PN rectifier type, so the UF4007, so this is an ultra-fast rectifier, very low junction capacitance, but quite a high 75 nanosecond of typical reverse recovery time, and we retest our circuit, well, our noise does increase a bit. We're up to about 1 volt of peak-to-peak noise. And well, this time, we have a clear negative spike. So this is occurring during the reverse recovery period. Now, the other main component of any converter is the transistor switch. This is a bit of a tricky subject to discuss, since the switch is supposed to, well, switch. We're talking about switching converters here. But the sharper the transition is, the more noisy the circuit becomes. So the choice of transistor and its driving circuitry needs to be a balance between efficiency and noise. So the first thing to consider is that power supplies can be divided into two big categories: converters, ICs that contain both the control circuit and the switch in a single package, and controllers, where the switches are external. With the converter, usually there's not much you can do. The transistor and the driving is more or less fixed. It's all inside of the IC, so you can't really affect the switching characteristics, though one notable exception occurs when the gate driver has a dedicated external capacitor, like in buck converters with a bootstrap. Here, although not really recommended, you can add a bit of series resistance to the capacitor to at least partially change the slope of the transistor. On the other hand, with the controller, it's a completely different story. Other than the internal parasitics of the driver and the transistor, you also have a bit of wiggle room. So if we come back to the simulator and use one of our older circuits, so the boost with an ideal diode, but replace the switch with one of the transistors from the library, and we run the circuit as is, we can have a look in the switching node and see that for the given driving circuitry, we are getting about 30 nanoseconds of rise time and about 8 seconds of fall time. Now, without changing the transistor or the driver, the thing that we could do is increase the slope. So here, the easiest and cheapest method is to simply add in a series resistor. So if we check the effect of this, we can see that both our rise time, which is now 42 nanoseconds, as well as our fall time at around 37 nanoseconds, have increased. But now, if you want to adjust the slopes individually, so maybe you just want the rising or just want the falling edge to increase, you can create a resistor diode network. So the idea here is that current goes one way through both branches, but it will go the other only through one of the branches. So if we check the results for these circuits, so the one in which the diode is pointing the right way, and the one in which the diode is pointing the other way, we can see that in reference to our single 15 ohm resistor circuit, only one of the slopes, but not the other, depending on which circuit we're analyzing, has changed. Now we could change both slopes or just one using something similar, but by varying the values. So now let's focus on the main element of a controller-based supply, the transistor itself. So here, there are a few things to look out for. Now, when looking over a transistor's datasheet, there are a lot of critical parameters to keep in mind. However, on the topic of the day, you should first look at the dynamic characteristics, and specifically at the transition times that the transistor presents. So you can always make the transistor switch slower, but you can't really make it go faster. And the other important aspect will be the various capacitances. Can you actually drive the transistor, and will your system be stable? So the MOSFET type of transistor has three main capacitances in between its pins. You have the gate source, the gate drain, and the drain source capacitance. However, the datasheet doesn't really mention these, but rather you get a different set. You have the input capacitance, the reverse transfer capacitance, and the output capacitance. The reason for this classification has to do with the way in which these impact the operation of the transistor. So when you're driving the transistor, you need to charge and discharge the complete input capacitance, then whatever voltage variation occurs on the drain has to also drive the output capacitance, and finally, the gate and drain are working inverted one in reference to the other, so you have a reverse feedback loop going through the reverse transfer capacitance. In general, you want all of these to be as small as possible to keep the converter losses reduced, but another important aspect to keep in mind is the ratio of reverse transfer to input capacitance. This should also be kept as small as possible for stability reasons. So one example to highlight why this capacitance ratio is important appears in a half-bridge arrangement. For example, you will find something like this in a synchronous buck converter. So for this circuit, I just kept the two transistors without the rest of the power supply, just a resistor to make things a bit more clear. Now if we run the circuit with a normal power supply, you will have two driving signals that are in phase opposition with a bit of dead time in between. And well, this produces a square wave at the output. Now, if we check the current going through the transistors, we will observe that other than the resistor current, which is a square wave, we are also getting a set of spikes, which are not really supposed to be there. Now, we can further isolate the problem by just driving the high side while leaving the low side gate connected to ground. And well, with this setup, our spikes are still appearing, and we can see that these are going through the low side exactly when the high side is being driven by the control signal, so on the rising edge. Another thing that we can also observe is that at this very moment, we are also getting a positive voltage spike in the gate of the low side transistor. And well, if this is high enough, it will be sufficient to drive the transistor into conduction. So with this setup, when there is an external voltage variation occurring on the drain, the internal capacitances are forming a capacitive divider, and the pulse will also appear in the gate. Now, of course, the various resistances are opposing this, but even if the gate is completely pulled to ground, there is still a non-zero amount of internal impedance. So if the capacitance ratio is just right and the pulse sharp enough, it will momentarily activate the transistor. And if this activation is strong enough, it can even lead to an oscillation event. And now we don't really want that, do we? Now, this phenomenon is impacted by multiple parameters. One of them being the slope of the voltage driving the high side transistor. So I created this other circuit in which I used a slower driver, so a larger resistor in the gate of the high side, which is creating a slower transition. And well, if we look only to the current flowing through the low side, we can see that for our second circuit, it does indeed become a bit smaller. It didn't disappear, but it did go from around 15 amperes to only 6. Now, another factor to look at is the exact voltage that is being switched. So with our initial circuit, we used 50 volts, but if we only change this to, say, 20 volts, we can see that we are getting a similar effect. The drain current in the low side is decreasing. The reason for this being that the voltage after the capacitor divider, so the one between the drain, gate, and source, is proportional to the voltage that's being switched. So with lower supply voltages, a smaller voltage is available to drive the gate. Now, although a bit more difficult to highlight in the simulator, different capacitance ratios as well as different transistor threshold voltages will also impact this phenomenon. Next thing to look at is the control circuit itself. Now, fundamentally, the control circuit needs to drive the switches based on the output voltage. So the duty cycle needs to be adjusted so that the output voltage is kept at the desired value. So regardless of IC choice, the switches will still switch and the supply will be noisy. But one of the important things that can be controlled, however, is the exact spectral distribution of this noise. So first off, when noise is concerned, it's important to choose a converter with pulse width modulation, not pulse frequency modulation. With pulse width modulation, the switching frequency is fixed regardless of load, whereas with pulse frequency modulation, the switching frequency is load dependent. And you can never really be sure of what the exact noise spectrum will look like under all possible use case conditions. Now, once you do choose a pulse width modulator, the next thing to look out for is the exact frequency of switching. So commonly, switch mode power supplies work somewhere between 50 kHz and 3 MHz. However, when choosing the exact frequency, other than looking at the materials and the component properties, the final important aspect to consider is regulatory emission limits. So the idea is that if you have a choice and the design is noise sensitive, it's a good idea to choose the switching frequency so that the fundamental does not rest inside one of the limits that you need to be below. This analysis can be taken one step further, and special attention can also be placed on the first few harmonics. The last aspect of the oscillator that needs to be considered is the implementation of some form of frequency modulation. So various ICs will implement different strategies for this. Two common names that you will find are spread spectrum clock generation and frequency dithering, but the fundamental idea here is that if your oscillator does not have a fixed frequency, the noise energy can also be spread out. This in effect makes the emission smaller, thus being able to help you pass emission tests without actually reducing the total amount of noise that you are generating. To highlight this effect, I created a rather simple setup based around the boost converter we looked at previously. So when we turn this on and come close to it with a magnetic near field probe, under normal operating conditions, we can see the emissions from it are forming a clear set of peaks. In this case, the fundamental is around 55 kHz, and then we see the upper harmonics. So this is the typical emission shape of a fixed frequency converter. Now this IC, the MC34063, like many others, does not support a built-in spread spectrum feature. But as long as you have access to the oscillator timing pin, you can usually affect its behavior. So for this experiment, I connected a large value resistor from the timing pin to the signal generator. And while the generator is configured to create a triangle wave. So if we now turn on the generator, we can see that first of all the center frequency shifts a bit. This is not really intended, but not much can be done about it. However, the useful phenomenon that is occurring is that the oscillating frequency is now variable. So we can see that it has spread out a bit, and thus the perceived emission levels are lower. So the same noise energy is being emitted, that did not change. However, since it's not a single frequency anymore, the peak noise value does seem lower. In the end, circuit design is not just about choosing the right value of components, but it's also about taking into consideration the more and the less common properties. With a real circuit, every parameter will have some amount of influence in the final behavior. Now, even if you do all of the calculations and choose the best components, it might still not be enough. So next time, I will be looking at some of the measures external to the power supply that can be taken. But until then, hope you enjoyed this video, and if so, there are more similar videos on my channel that you might want to check out. And if you want to be up to date with my latest releases, also consider subscribing. See you next time. Bye bye.